I'm here to answer questions if anyone has them. Pardon me. You will notice I'm in my closet. My dogs have been kind of anxious and running around this afternoon for some reason, so I'm in here because it tends to be the quietest. They don't come in here a whole lot. So feel free to ask me questions. I'll be sitting here doodling until I get something. Sure, I'll take some tea. Why are you all wet?
I was washing something out. It was the ice cube tray.
Were you talking to someone downstairs?
I was trying to talk to my mom, but she didn't have much reception.
Oh, okay.
What tea would you like?
Surprise you?
No, I don't surprise.
Come on.
No.
I don't know what I want. Something without caffeine, something herbal. Just pick something herbal. Okay. Sorry. Tea connoisseur problems. Delcus, I do not have the book with me. Can you tell me what the problem is? Or take a picture of it and email it to me? Or give me something similar that I can work on with you? Alright, yeah, just email me and I can look at it. Sorry, I have the 9th edition and the 8th edition book. I keep the 9th edition at school for you guys, so I have it with me, but I have the 8th edition at home and the numbers don't correspond the same. I'm not seeing it come through yet, but when that comes, I'll answer that. Are there any other questions? I see there are 5 of you guys logged on, so presumably some of you have some questions. Oh, I got the new teacup? Well, that's exciting.
Careful, it's easy to spill.
A new teacup. kind is it?
There's almost cinnamon in it.
Okay. Thank you. Okay. Well, as we wait, I'm going to doodle pictures. Delcus, I haven't gotten it yet. Did you send it yet? I just refreshed my email. Didn't let you send it. Send it to my email? Well, if you have another email address, you can send it from that. Hybridizing. Okay, so while we're waiting on Delcus's, because I still haven't gotten it yet, I'll answer Jonathan's. Dr. Mann, for the hybridizing atomic orbitals, if you have a molecule with an sp3 and an sp2, how does one determine the angle between them if the sp3 is 109.5 and the sp2 is 120? Okay, so the thing about that is that you're really looking at the angles that are between the atoms connected to a specific molecule or to a specific atom. So let me, oh shoot, hold on a second. Let me pull this up. So, for example, if I have something like the, oh shoot, hold on, brush. If I have just a regular carbon that we would think is sp3 hybridized, right? And then it's attached to a carbon and a nitrogen that would be sp hybridized, for example. You're not looking at any other bonds other than the bonds that are attached to this carbon would be 180 degrees from each other. So that right there would be 180 degrees, okay? Whereas this angle here would be the 109.5 approximately that we would expect, because they're attached to the same carbon, so they would be part of that same hybridized kind of system. Did that make sense? These two would be 109.5, those two would be 109.5, and those two would be 109.5. So you're really only comparing it to the other atoms that are attached to a very specific hybridized atom. I hope that makes sense. Let me know if that doesn't make sense. I'm going to look to see if Delcus' stuff came through yet. Delcus, I'm still not seeing anything, hun. Can someone give me the type of question she's asking for? It was... see if I can find it. She said it was problem... homework, chapter 2, question number 24. Double check, make sure it didn't go to spam. No. Oh wait. Got it. Okay, hold on. Delcus, you sent it to me, and it's upside down. So hold on a second. I gotta predict the products of the acid-base reactions. Okay. Hold on a second. You guys have to understand I have about 45 windows open to do this, so it can be a little challenging to organize that. Okay. So 224. Are you talking about letter A, Delcus? Because if it's letter A, that's Lewis acid-base chemistry, and we didn't cover that one yet. It's in the book, and I mean, you can read the book on how to do it, but we haven't covered it yet. I can talk about letters B or C, if those are the ones that you're having trouble with, but if it's letter A, I'm going to tell you to hold off on that for another few weeks. What is that yes in response to, Delcus? Oh, wait a second. My computer just said that you said yes, but you didn't say anything, so hold on. It's a very special system I've got running here. If you're looking at Lewis acids and bases, they're generally something that we look at them from the context of having electrons to donate. I feel like they're confusing when we haven't... Yeah, I mean, it's in the book, so I figured you guys could read through it to kind of get a background on it for when we do cover it, but I don't ask questions about those on our first exam. The deal is that boron and aluminum have what's called an open shell right there, where they don't have any electrons and they don't have an octet because they have a weird valence. Their valence is 3. So they can actually accept electrons from something, making them a Lewis acid, because Lewis acids are electron acceptors. So, yep. All right, next question. There are 9 of you. What are your questions? Y'all are being very quiet tonight. Jonathan, yes. Isomers have different arrangements of atoms, and resonance is their rearrangement of the pi bond and lone pair electrons. So the core of the molecule has to stay the same. Everything, the connectivity as we call it, has to stay the same. You can't move a hydrogen, you can't move a carbon. You can only move double bonds or pi bonds, double bonds, triple bonds, and lone pair electrons. So it's a common question. Some people get resonance structures and isomers confused because they do look like different versions of the same thing. But, so let me draw you a picture here for an example. Okay. So let's say I have 2 molecules here. This one's ethanol. It's got 2 carbons and an oxygen. And I'm comparing that with something called dimethyl ether. Okay. One of those is a surgery. Oh, I actually don't know if they use that one for surgeries, but one of them will get you drunk and one of them will make you pass out. Ethers used to be used as surgery, anesthetics, and things like that. So they're very different molecules. They have very different physical and chemical properties. And so they're not really considered anything close to the same other than they share the same formula. Now, if I look at something like, let's see, like this, where I have a possible resonance structure. These are considered variations of the same molecule, not different molecules entirely. So that's kind of where the difference is. I realize at this point, because it's new to you guys, it probably just feels like we're splitting hairs, but because these 2 molecules are constantly in kind of flux between, or these 2 forms are constantly alternating between each other, you can't purify one from the other. They have the same properties because they're the same molecule, whereas the ones that I drew above are completely different molecules with different properties. So I hope that explains or answers your question. Pardon me. Okay, Andrew asks, Dr. Mann, could you talk about separation of charge again with resonance structures? I can. So let me go back to my paint window. Sometimes it's easier to do this on ChemSketch and sometimes it's easier to do it on Paint. So here we go. All right. So let me think of a good example for you. Sometimes there's resonance structures that have kind of equivalent stability, okay? And then sometimes there's resonance structures that don't. They're less stable, because they don't have, or because they have what we call separation of charge, meaning you took a bond that had no charge and you moved it to make a positive and a negative charge. Okay? So if I were to take, let's see. Alright, so let's just take, actually let me do this one. Alright, so in this case I have just a carboxylic acid that's been deprotonated, right? So if I move, I wonder if I can change my color, there we go. So if I move some electrons in there and move some out, right? Then I get one of the resonance structures. And we would say that this would be an equivalent resonance contributor because they have kind of the same look, the same charges on the same atoms, right? But what if, and bear with me on this, what if I move these electrons back out? Okay? And I don't move the other ones in with it. Then I get another possible resonance structure because I have moved pi bonds, right? Pi electrons, and made a negative charge on that oxygen. That oxygen still has a negative charge. And the carbon that it was attached to has a positive charge and is missing an octet. Okay, so we basically put a formal charge on two different atoms in the molecule as part of that resonance structure, okay? These two here would be good. And then this one down here would be unfavorable because it's going to have that separation of charge. Okay. Does that make sense? Let me know if that makes sense. I just got an email. Let me see if it's one of you guys. No. Okay. YouTube was emailing me to let me know that there are people looking at my channel right now. Really? You don't say. All right. Jonathan, or yeah, Andrew, can I get comfort? Okay, great. I was going to say, I just need confirmation that that made sense. All right, so Nicholas said, the ammonium ion has a lower pKa than methyl ammonium in their corresponding conjugate bases, which is the stronger base. Okay, so if you look at that sheet I gave you earlier, actually, you know, it shows you that if you have basically a low pK, goodness gracious, there we go, low pKa, then the conjugate base is going to be a very weak conjugate base. That's supposed to be a CB, sorry. Okay. So you basically have to just like compare them. So if ammonium has a lower pKa, so that means it's more acidic, right? Than this molecule. Okay. Then the conjugate base of this would be ammonia. The conjugate base of that would be methylamine. Okay. So the stronger the acid, the weaker the conjugate base. So the weaker the acid, the stronger the conjugate base. All right, and it's just this relationship that goes back and forth. If I have HCl, right, its conjugate base is literally just chloride ion, right? That's a really strong acid, and chloride ion's not a good base, right? It's in sodium chloride. You use it to, you know, keep your body functioning. On the other hand, if I have water, which is a much weaker acid than hydrogen chloride or hydrochloric acid, the conjugate base of that is hydroxide, which is very, very strong, right? That's a strong base. So you're basically looking at, if something is a stronger acid, it has a weaker conjugate base relative to something that's a weaker acid, which would have a stronger conjugate base. Does that make sense? Derek, you said you were watching, but that you didn't have an account, so you couldn't send a question. Oh, good, Nicholas. Awesome. But, I mean, you can send me an email question if you have one. I do have my email window up. Sue? Yansu, is that you? I don't know anyone else with that last name. The pKa value table, no. I expect you to know that. The one that's just the little number line that I gave you guys, though. You don't have to, like, look at that whole list, okay? If you needed a very specific number, I would provide it for you. And the periodic tables are on the wall, so I'm not taking those down for the exam. You'll have full access to those. More questions? Connectivity is just, okay, so you mentioned connectivity multiple times. Would you mind talking more about connectivity? It's literally just the kind of arrangement of atoms, how they're connected to each other. Is it a carbon-oxygen-carbon or carbon-carbon-oxygen? That's really it. It's just how things are connected. So isomers are connected in different ways because they don't basically have the same skeleton, right? The atoms are in different placements. Okay, Derek just asked the question, will we have access to the table of acids and conjugate bases for the exam? No. The only ones I need you to know are the ones that we put on the number line in class the other day. So you need to know what a strong acid is and a strong base. I expect you to know those and know that list, which was pretty small. And then you need to know what carboxylic acids, protonated amines, water, alcohols, amines, and hydrocarbons. Those are the ones that I need you to know the essential placement of for the exam tomorrow. I'm gonna give you guys Twinkie time. I have a dog named Twinkie. He's laying on the floor next to me in my closet. He's named Twinkie because he's a Corgi Husky mix, so he's like 85 pounds on 6-inch legs, and he's yellow, so he kind of looks like a Twinkie when he walks around. Okay, Derek said, so we don't need to know what the pKa of a deprotonated carboxylic acid would be. No, there is no pKa for a deprotonated carboxylic acid. The pKa is the ionization of an acid. So if there's no hydrogen on there anymore, it can't have a pKa. It could have a pKb, meaning the dissociation and whatnot of the base, or rather the ionization of the base. But, pardon me. But yeah, we, like, if I have, pull up that window again, where is it? If I have HCl, right? And so when that ionizes into H plus and Cl minus, this has a pKa of less than 0, okay? This one doesn't have a pKa because there's no hydrogen left, right? So you can only have a pKa if there's a hydrogen on there. Now, there are some molecules that have multiple ionization states, right? We call those polyprotic acids. And so an example of that would be ammonium, because we could lose one proton from that, and technically we could lose another one. Now, the NH2 minus is really, really, really basic. It's considered a strong base, and it's way down that line on the pKa table. So, you know, the NH4 plus is going to be, you know, 8 to 10-ish. The amine is going to be in the 30s. And we can't even have a pKa really for the NH2 minus because it's not going to be able to be deprotonated. So we don't need to know the pKa value. Why did it send me the same message twice? Hold on a second, Derek. Roger, Dr. Boy, Roger. Yes, okay, good. That made sense then. Nicholas Terra, do we have multiple choice questions? No, I don't usually ask multiple choice questions. There's nothing on the exam tomorrow that we need a calculator for. I mean, I guess if you want a safety blanket, but I don't have any, I wrote it, there are no numbers on it other than pKa values. So, no, you don't need a calculator. What atoms associate with inductive effects? So, inductive effects are for electronegative atoms, right? So, if you pull up, let me see what we can Google to find that. If you look at electronegativity chart, maybe, if you Google that, you can pull up the values for electronegativity, and you can kind of see which ones are pretty electronegative and which ones aren't. So, you know, fluorine has an electronegativity value of 4.0. Oxygen, nitrogen, chlorine, and bromine are all considered fairly electronegative. So those are the ones that you would be looking for regarding inductive effects. Everything else is going to not really lead much as far as inductive effects goes. Now, later on in the semester, we'll talk about carbon helping stabilize other carbons with charges, which is kind of similar. But when we're talking about acid-base stuff and inductive effects, we're really looking at things that have electronegative atoms defined as nitrogen, oxygen, fluorine, chlorine, and bromine. Oh, good, that made sense. Next question. There's about a 15-20 second lag. And so after I record, if I have the right window popped up, I can see myself kind of talking to you guys, but I have it on mute so you don't get it in this weird loop hearing it. But it's weird to watch my head keep bouncing back and forth because I have 4 different screens up in different corners of my computer. What's up, Twinkie? You're a good puppy. You furred on my floor, dog. Hi, Lindsay. I'm just doing 4 pages. I thought about 6, and then I thought that's mean, that's a lot, so I'll do 4. And that way, you know, we can get done a half hour early tomorrow, and then maybe we could even start lab a little bit early. That way we could get done early. go over resonance for diazomethane, please. 57 part D. Let's look. Diazomethane. Oh, that molecule. Okay. Sometimes we have different ways of naming things. All right. Oh, hold on. Which screen do I want? I'll do this one. So diazomethane be CH3 down to that. Oops. And then, oh wait a second, I put on too many, didn't I? Goodness gracious. Let me fix that. There we go. So those are supposed to be my lone pair of electrons. It's kind of hard. Now, if we came up with the formal charges for this, you would see that it would have a negative and a positive, right? So where can I move electrons? Okay, I can't move electrons to make something bigger than an octet, right? There's no orbitals to fit those electrons in, so we cannot supersede and go past an octet on things that don't have d orbital shells open. Okay, so if I took one pair of these electrons on nitrogen, and let me change my color here, and moved those in to form a nitrogen-nitrogen double bond, that would put, 10 electrons on the middle nitrogen. So we would have to move those, and I can put them on the CH2, okay? So that's kind of a hard one, but we can answer it. That CH2 now will have a lone pair of electrons on it, right? And if a carbon has a lone pair of electrons, it's going to have a negative charge because its valence would be 5 instead of 4, so 4 minus 5 is negative 1. The nitrogen is still there, right? And now it has a triple bond to another nitrogen. Now, what you've essentially done is moved this charge, that was supposed to be purple, that doesn't look purple at all. Let's try blue. Make it a little bigger. What we've essentially done is taken that charge and moved it out to there. We haven't changed where any of the atoms are, but we've essentially helped disperse that charge throughout the molecule. Now, there's another possibility for a resonance structure that I'm not going to cover, which would include separation of charge, but it's one that we wouldn't really see. So I'm going to leave it at that. But let me know if what I just drew makes sense to you, okay? I'm assuming that was one in the book. I just got your email, Emily. Hold on. Yeah, you got it right. It looks great. Ooh, your resonance structures are pretty. I'll be honest, it upsets me a little when my students have better looking handwriting than I do. It's okay. I've come to accept the fact that my handwriting's not pretty. But yeah, those look great. Another example of separation of charge. Okay. We'll do this one. So what if what if I took this bond and moved it onto the nitrogen? Okay. It's going to give us a little something different, right? I would still have my CH2 here, with a negative charge. I would still have my bond to my nitrogen, and now I would have 2 bonds to this nitrogen, and that would have a negative charge again. This nitrogen in the middle is missing electrons, and that would end up with a positive charge. Okay, so because of that, we would call that separation of charge. Instead of having instead of having 2 charged atoms, we would end up with more than that, right? So it's basically when you're taking a charge and moving it to something else, or taking something that's uncharged and making it have a charge on it. Let me do another one, because I think that we can show this a little bit easier. So let's say, let's just do something real generic. I'll do X double bound to Y, okay? That's supposed to be a Y. Okay. Now, they both have whatever electrons they need around them to fulfill their valence so that they don't have a charge. If I move a bond on that, okay, that Y is now going to have more electrons than it should, giving it a negative charge because electrons are negatively charged. And the X will have a positive charge because it's missing electrons that it needs. Okay? Alternatively, we could have done something similar where we put the bonds on the X and it would have been the same thing. Okay? So if I said which of these molecules is more stable, well, it would be the one that doesn't have any charges on it, period, right? Charges are a destabilizing force on a molecule, okay? So, Lindsay, let me know if that makes sense. But it's basically just taking something that doesn't have a charge, and it's usually going to be moving a pi bond so that it splits up and has a positive and a negative charge on it. Okay. Andrew says, would you suggest going over the practice test that you posted or doing more of the homework problems in the book? Both? I mean, I think that, going over an old test can be useful. The old test that I posted had some problems from chapter 3 in it because we covered it a little bit last semester before the first test. So, I mean, I think it's always good to kind of get an idea of what types, how I phrase things, what type of questions I ask. But the problems in the book help with a lot of the theory about things. So ideally you would have all of them done. Did I lose you guys? Are you teetering off? Are there no more questions? Oh, hi, Kara. Can you go over what exactly the bond angles do or look like in hybridization? I'm not sure I know exactly what you're asking me. What exactly bond angles do or look like in a hybridization? this might be an insufficient answer for you. Can I tell you that we'll get to that within the next week? We're going to start working with model kits very soon, starting in Chapter 4, which will be starting on Tuesday. And we'll look at a lot of the bond angles and things like that for different hybridizations. So when we draw them, I'm not, expecting you guys to have perfect bond angles or anything right now. You can draw things just straight lines if you want. You don't have to have anything wiggly or bent or anything to mimic that. The only thing I need you to know at this point is an sp3 hybridized atom would have roughly 109.5 degree bond angles with tetrahedral geometry, that kind of stuff. We will have a lot of practice with drawing them with perspective drawings so that we can actually indicate and show those bond angles, but we won't get to that until next week. So for now, would it be sufficient for me to tell you I just need you to know what they are so next week we can actually implement that? That might be easier than trying to cover all that tonight since we don't really need it for the test tomorrow. I don't normally pull the let's wait and do it later, but it would be a lot easier if we had a model kit in my back pocket, and I do not have a model kit in my back pocket to show you. I can do that, Emily. Hold on just a second. I have to look it up. Exam 1 from spring, right? So, Yansu, I don't have the book with me. So if you want me to look at a very specific problem, I need you to take a screenshot and email it to me. Okay, so 13, question 13. Hold on. So, Emily, are you talking about the one that has an alcohol on it? Or the one that has a protonated amine? The one with alcohol wouldn't have a resonance structure. Not every molecule can have one. The one that has the protonated amine just has the same resonance that we talked about for benzene the other day. So the nitrogen wouldn't have any influence on the resonance of that because it doesn't have lone pair electrons or pi bonds. Emily, can I get some feedback? That would probably be, there she wants it. Okay. Okay, Yansu, the first one, I actually talked about that at the beginning of the video. That is for Lewis acid-base chemistry, which we actually didn't get to yet. I didn't want to add that on since in the summer things are so quick. So don't worry about 224A. We will get there. As far as 224B goes, pull up my paint. So I have acetone plus hydroiodic acid. Hydroiodic acid is a really, really strong acid. It's pKa, I think, is like -9, -10. It's up there with sulfuric acid. So the question is, if we donate a hydrogen off of that, we know we're going to get iodide, right? Well, where's the hydrogen going to go? Well, it has to go on something that has a lone pair of electrons to grab the hydrogen, okay? So essentially the only thing you could get would be that, because there's nothing else that can grab that hydrogen. And Emily, the one with the protonated amine, as I said, the amine isn't going to be able to participate in any of that because it doesn't have a lone pair of electrons or a pi bond. So instead, you're going to be looking at the benzene ring. Where these electrons are going to move around the ring. And I mean, we showed this the other day in class, so you should have that in your notes too. Now, I could have drawn them clockwise or counterclockwise, it doesn't matter. We do have the option here, if Lindsay's still with us and curious, we do have the option here of separation of charge, because I could move out one of these bonds. Let's say I'll put it there, and I'm putting it on the carbon instead of between two carbons. If I do that, I would end up with that bond there, and then now I would have a negative charge with a lone pair on that carbon and a positive charge on the one next to it. So that could be an example of a bad resonance contributor or a less useful resonance contributor because it has separation of charge. And you could actually do that on any of those 3 double bonds that are on that molecule. But these two here are the most important resonance contributors for that molecule. I asked myself when finding the acidity due to the 5 factors. With induction, you asked, is there an oxygen, fluorine, or chlorine present? Sure. So let me change that. I can put in text. Is the atom in a lower period? So, you know, usually if you're talking about things like, well, like think of it in comparison to organic atoms, right? The ones that we use in this class, so, or in this discipline. So carbon, oxygen, nitrogen, hydrogen, fluorine, those are all very small. They're in that very first couple periods of the periodic table. But once you get down to like iodine and chlorine, iodine, chlorine, bromine, those tend to be very large. So those are the ones that I tend to look at for size. Or if I'm comparing to like something that has a sulfur versus an oxygen, but everything else is the same. You know, the sulfur's larger than the oxygen. So I just kind of look to see if that follows the trend of size. And that just kind of depends on the specific question. Electronegativity. Is the atom let me try this. Is the hydrogen attached to a nitrogen, oxygen, chlorine, fluorine, bromine? Did I miss one? No. Yeah. So if it's basically that, which is the same as with inductive effects, so does it have a nitrogen, oxygen, chlorine, fluorine, or bromine somewhere else in the molecule, not connected to the hydrogen? Then stretch that out. For resonance, are there pi bonds or lone pair electrons that can be moved to help stabilize the molecule after it loses a hydrogen, right? With this, we're always looking at it from the aspect of losing a hydrogen because we're talking about acid-base chemistry. So, you know, everything is with regard to, does it stabilize the conjugate base? If something can make a good, stable conjugate base, it's more likely to donate off one of those hydrogens. Number 5 is, what am I missing? Charge. Is there a positive charge on the atom attached to a hydrogen? And we see that a lot with nitrogens, but you can also see it with oxygens where they have an extra hydrogen on them, giving them a positive charge. If we take off that positive charge, we make the molecule more stable. So those are basically what I asked myself. That's probably very similar to what you have in your notes, though. I don't know how useful that is for you. Hopefully that helps a little bit. Lindsay says, what are some things to keep in mind in order to draw constitutional isomers quick and efficiently? Okay, so Lindsay, that's a great question because a lot of people have a lot of trouble doing that quickly. To me, it kind of reminds me of in general chemistry with balancing equations. It always seemed like with balancing equations, you know, it's really, it can take a lot of time if you have a really big one. So I understand that. Ow. Okay. So for me to do it quickly, I draw different kind of scaffolds. Okay, so first off, I find the units of unsaturation. So let's say I have two units of unsaturation. I really need to get a stylus for this screen. Okay, and then let's say that I have 3 carbons and an oxygen. Okay. And really, we're looking at anything here that's not hydrogens, okay? So I just drew them in a row. It doesn't matter how I draw them, but for 2 units of unsaturation, I need either a triple bond or a double bond or, 2 double bonds or a bond and a ring. Well, it's going to be a little bit hard to find a double bond and a ring. We could do it because we don't have many atoms, though. But basically, after you get that down, everything else, all you have to do is put in the hydrogens that give it the number of bonds it's supposed to have. So carbon needs 4 bonds. This carbon already has 4 bonds. That one needs 2. And that one needs 1. So this, if I'd given this to you, the formula would have been C3H4O. All right? Well, so let's try and do another one, right? C3H4O. Let me do this. Kara, we'll get to more isomers next week. I keep saying constitutional isomers because there's lots of types, but that's the only one we need to know right now. So another option, instead of putting 3 carbons in a row and an oxygen, let's do 2 carbons in a row and an oxygen and another carbon, right? And then we can put in, you know, 2 units of unsaturation. Well, okay, where do I want to put them? I guess I'll put them there as a triple bond. That's really the only place I could put it on this one, because if I tried to put a double bond between the carbon and oxygen, that would have put too many bonds on the oxygens. But after that, I just have to fill them in, right? And it'll give you the same thing every single time. Wait, you can't see that? Let me see, what did I do? I'm sorry, I didn't scroll over. I'm really glad that you said something. Let me try that again. I am so sorry. Let me change the color on that. All right. So what I was trying to say is if I have C3H4O, okay, let me know. Can you see that now? And that has 2 units of unsaturation. Okay. And so then I can take those non-hydrogen atoms and arrange them in a variety of ways. Okay. So I can put them in a straight line, right? I could put them not in a straight line. I could put them in some sort of ring with an oxygen coming off, or I could put the oxygen in the ring. Okay. That is not accounting for the units of unsaturation, so I have to put those in. Well, I could put double bonds there. That's 2 units of unsaturation. I could put a triple bond there. That's 2 units of unsaturation. The ring already has 1, so let's put on another. That's 2 units of unsaturation for the double bond. And then everything else I have to do, I just put in the hydrogen. So carbons need 4 bonds, so I put on 2. That carbon here already has 4 bonds. That carbon there has 1 needed. This oxygen needs 1, right? So you don't even have to really think about the hydrogens. I mean, you can kind of check your work on it. But if you have a skeleton of, you know, the atoms plus the units of unsaturation added in, you're not going to get it wrong, okay? The biggest problem, though, is people will freak out and panic and just start putting in all kinds of random stuff that doesn't make any sense. They'll put extra atoms on carbons that shouldn't be getting them. And we don't really need to be doing that. So hopefully that makes sense. A little bit, you know. Let's do another example. So I didn't mean to scroll down so fast, sorry. There we go. So let's say I have C3H6O, okay? The easiest molecule for that most people would be familiar with would be acetone, okay? Where it's 3 carbons with a double bond to the oxygen in the middle. But that's definitely not the only way we could orient those, right? We could have a ring with an oxygen on it. We could have a 4-membered ring with an oxygen on it. We could have the same looking molecule, but where the oxygen is at the very end instead of in the middle. Now be careful, because this is exactly the same thing, is that it's just been rotated by 180 degrees. So that's a really big error that I also see people make, or that they will just like change the bond angles and think that that's a completely different molecule. They're not a different molecule. They have to actually be connected differently, okay? Does that help? Does that make sense? But I mean, that's how I do it. And your book doesn't cover units of unsaturation early on with you guys. It waits until much later on in the book, and I don't know why, because I think it's the easiest way to kind of get an idea about what a structure should look like when you're talking about doing isomers. 2, 3, 4. Oh, that's a good one. Let's look at C2H4O. How many units of unsaturation does that one have? Somebody figure it out for me. Twinkie, you are precious. No one? Okay. C2H4O, so 2 times 2 plus 2 would be 6, right? So 6 minus 4 is 2, so yeah, thank you, Delcus. Thank you. 1 unit of unsaturation. As I said, there's a delay, so I don't know how long you guys have been working on that. It seems like 4 minutes to me. So 1 unit of unsaturation. Okay, so, well, let's just put these in some sort of line. Okay, that's an option. That's a different option, right? That's a different option. Okay, so those are 3 kind of different connectivities, meaning they're connected in different ways. The core of the molecule is connected in different ways. So then after that, we still have 1 unit of unsaturation to account for. In the ring, we've already done it. So then we would have 2 hydrogens here, 2 of them there, and we're done. This one here, oh goodness, I can't do that one, can I? If I put a double bond on one of those, that wouldn't work. I'm sorry. Let's see. But I could do a double bond there. There we go. So that's another option. So that particular formula has 2 different possible isomers for it. Okay? And sometimes you might do what I did. Like you might find out, oh, with this skeleton, it won't be able to fit the units of unsaturation, right? But most of the time it will. So most of the time it's not an issue. So just kind of consider that when you're working on them. I'll take one more question. And then you guys need to go study. And I need to work on the worksheet I need to give you tomorrow. Alright, kids. I'm cutting the cord. We're done. No more questions. If you have more questions tonight, I try to go to bed in the summer by midnight because of class. So if you try and email me before midnight, I should be able to get back to you. But if you get that later than that, I can't guarantee that I'll be awake to answer you. But I hope everybody has a good night. Study hard. The exam is 4 pages. 2 pages from chapter 1, 2 pages from chapter 2. You know, the problems are very similar to what are on old tests and the problems that I put on the problem sets for you guys. Kara snuck in a question. What's the difference between S and sigma bonds? Is that S is atomic and sigma is molecular? Yes, that is the difference. So, but, and P and pi bonds, you know, it's kind of a similar thing. Pi is for bonds, so molecular orbitals, whereas P is the atomic orbital. So, anyway, I will talk to you guys later. I will see you in the morning. come happy with your bells on, I guess. And I'll talk to you then, okay? Have a good night, everyone.